Okay, in this screencast, we're going to analyze a complex circuit, and by complex, that just means it combines both resistors that are in series and resistors that are in parallel in the same circuit. So we'll have to figure out a method, procedure to follow to be able to simplify that circuit and figure out what the current is in each little branch. Before I start on this, though, as I watched the previous screencast, I realized I didn't define the units of voltage and resistance. So the units of voltage, the variable is a V, and the units are volts, which are also a capital V. That's a little bit confusing because you've got both the variable V and the units are also a capital V. So that's a little bit confusing. You can think of things like force, where the unit is a Newton, but the variable we use to show force is a capital F. So this one, capital V, is the variable and the unit. Resistance is measured in ohms. First of all, the variable is a capital R, as you gathered, I'm sure, from Ohm's law. But the units are ohms, and we use a Greek letter omega for that. Okay, sorry I missed that in the last screencast. Also, I noticed as I watched that the microphone, there was a lot of rustling. I had the iPad flipped around so the microphone was facing my arm, and every time I brushed against it, it made a noise. So I'm going to fix that for this one. Anyway, so here's, let's move on and we'll talk about how we're going to simplify this thing. It looks very complicated and it's not going to be too bad. We just have to have a way to approach it that will allow us to systematically simplify this one step at a time. The first step is we're going to take all the resistors that are in series, where the current has no alternative but to go one direction, and we will simplify those. First of all, let's notice that the current is going to come out of the positive terminal of the battery and head this way. We'll call this I1. Okay, so I1 passes through those two 5 ohm resistors on top. It comes to this junction right here, and then it splits 3 ways. We'll call this portion of it I2, and that's going to go all the way down through here. This will be I3 through the 5 ohm resistor in that branch, and then this will be I4. And you can probably see that these 3 are going to come back together again. I2, I3, and I4 at this bottom junction here, they're going to come back together to form I1, and I1 will come back into the 12 volt battery, and so charge will be conserved. The relevant equation for this is that I1 will be the sum of the 3 other currents, because we have to have conservation of charge. So all of the current going into one node has to be equal to all the currents leaving that node. So the first step, as I mentioned, is going to be combining all these series resistors, because I1 has no choice but to go through these two 5 ohm resistors. So if I combine those two into one equivalent resistance for those two resistors, it's like having one 10 ohm resistor right there. So this would be like a single 10 ohm resistor on top. And this, likewise, in this branch right here, I2, which passes through these two 10 ohm resistors, doesn't have anywhere else to go but through both of those. So those are considered series resistors. So between these two 10 ohm resistors, that's like having a single 20 ohm resistor there. Likewise, I4 has nowhere to go but through those two 5 ohm resistors. So we find the equivalent resistance of two 5 ohm resistors in series, and that's like a single 10 ohm resistor. So now we can redraw this, and we can actually show a more simple circuit by combining those 3 pairs of series resistors into single resistors. And I've done the next slide. So there's the more simplified circuit, along with the simplification step number 1, combine all of the resistors in series, or all the series resistors. So that's what we've just done. So I've kind of already shown that step on the last page. We're going to go to step 2 now, which is going to be working from away from the battery towards the battery. So in this case, from right to left, we're going to combine the parallel resistors. So simplification step 2 right here is simplify the parallel resistors working from the farthest away from the battery towards the battery. Let me just check what those resistors are. I thought I had them written down here. Okay. Excuse me. Okay. So now we're going to work on these resistors out here, the 20 ohm resistor, the 5 ohm resistor, and the 10 ohm resistor. And we're going to find out what the equivalent resistance is of those 3 resistors that are in parallel. Remember the equation for equivalent resistance for resistors in parallel. It looks like this. The inverse of the equivalent resistance is equal to the sum of the inverses of the individual resistors. So I have, I guess a common denominator would be 20ths. So this 1/5 would be 4/20, 1/10 would be 2/20. So I have 1/20 plus 4/20 plus 2/20, and that would be 6 7/20 would be the inverse. So the equivalent resistance, I'm going to take this up here, the equivalent resistance would be 20/7. I'll put that into decimal form. That is 2.86 ohms. Okay, so 2.86 ohms is the equivalent resistance. So now I can actually rewrite, make this even simpler by showing a single resistor in place of those 3 in parallel that has 2.86 ohms of resistance. I think you'll see where we're going with this after the last step. When we combine all of these resistors into a single resistor, that will allow us to calculate the amount of current coming out of the battery and going into the battery, which we defined as I1. Once I know I1, I can come back and figure out all the current in the individual branches by using what we know about the equivalent resistance in those branches and the current coming into those branches. All right. So simplification step 3 is we're going to combine the remaining resistors in series to find an equivalent resistance for the whole circuit. Well, so those 3 resistors that were in parallel are the same as a single 2.86 ohm resistor that is all by itself. Now it's in series with the other 2 10 ohm resistors. So the equivalent resistance for the whole circuit, taking the last 3 resistors that are in series, is 10 plus 10 plus 2.86. Remember, I can just add them when they're in series like this. So that is 22, actually. Shoot. 22.86 ohms. So that's the equivalent resistance for the circuit. So now my circuit, it's as if I have a single 22.86 ohm resistor here, and it's as if I have and I do have a 12 volt power supply. So I can very easily find what the current in this circuit would be, and it turns out that the current coming out of that battery in my simplified circuit is the same as I1 down here. So when I find this current up here, I'm basically finding I1 in my actual circuit. So let's go ahead and figure out using Ohm's law, V equals IR. We'll find, So I is equal to V over R, which is 12 volts over 22.86 ohms. So that's going to give us a current of 0.525 amps. Sometimes you'll see that expressed in milliamps. 0.525 milliamps. Or 525, I should say, milliamps. Okay? Either one, it's the same number. It's just different units to express it. So that's the current I1. So I now know that coming into this junction, I1 is 0.525 amps. And I know it splits into I2, I3, and I4. So now I can do a little analysis here to figure out what is the current I2, I3, and I4, which we'll do on the next slide. Okay, so I've just kind copied everything down from the previous slide. The 0.525 amps coming in to the branch, to the junction at this point right here. And I've got 0.525 amps coming out of that junction right there. We know this is the relevant equation, that those three currents have to add up to I1. And we also know what current is coming in, 0.525. We know the resistance in each one of those branches, but I've got three unknowns in this equation, so that's not completely useful. So we're going to use Ohm's law, but first we have to find the voltage across the three resistors in parallel. Resistors in parallel always have the same voltage across them. So the voltage at this point on top and the voltage at this point on the bottom, top and bottom there, we would like to know the voltage at that point. It's also sometimes called the potential at that point. The word voltage and the word potential mean the same thing in the electrical world. Well, in order to do that, I have to figure out, of my 12 volts that I start with, we're going to say this is 12 volts right at the battery, right here. That is 12 volts at the battery, and this is 0 volts on the bottom. How much of that 12 volts did I lose when, how much of that energy did I lose when I went past those two resistors? Well, each one is going to drop a little bit of that 12 volts. Combined, I'm losing, you know, the equivalent of the voltage drop is I times the resistance of those two together. So I'm going to say the voltage drop across the 5 ohm resistors, each one, is equal to the 0.525 amps times 5 ohm resistance. And that's going to be 2.62 for each one. That's 2.62 volts of lost voltage, okay? So that's times 2. So 5.24 volts is lost across those two. So that means the voltage at this point right here is 12 minus 0.5 or 5.24, which is 6.76, I think. That's 6.76 volts at that point right there. But notice I'm also going to, this point will not be 0 down here at the bottom. This bottom point won't be 0 because I'm going to lose another, let's see, 10 ohms. I'm going to lose another 5.24 volts right here. So, and that gets you down to 0. So the voltage at this point must be 5.24 volts. So let's just summarize that. Okay, just to explain what I just did, I said I know I've got 12 volts at this point right here, leaving the battery, and I lose of that 12 volts, you can think of it electric potential or energy. I'm going to lose I times R across these two resistors. I know the I, I'm looking at the resistors on the top here, those two guys. I know I've got 0.525 amps going through each one of those, so I took 0.525 times the 5 ohm resistance. That gave me a voltage loss of 2.62 volts, and there's two of those, so I lose, of the 12 volts, I lose 5.24 volts across those two resistors, which leaves me at this point up here at the top with 6.76 volts. On the bottom, it's just the opposite because I'm going to end with 0 volts at the negative terminal, and I know I'm losing, at this point right here, I'm losing V equals IR here. I'm losing 0.525 times 10, 5.25. I don't know why I got 0.24. I guess that's from rounding. 5.25 volts of voltage lost across that 10 ohm resistor, which means back here at the bottom junction, I must have had 5.25 volts of voltage left, of potential left at that point. the reason I'm doing this is I want to know what's the potential difference across my three branches here, and I can find the voltage difference from top to bottom by subtracting this 6.76 number and this finding the difference between 6.76 and 5.24. Let's do that. The voltage drop across those three resistors is 6.76 minus 5.24 is 1.52 volts. Okay, so of the 12 volts, let's look at it this way. Of the 12 volts, I'm going to lose 5.25 volts across the top two resistors. I'm going to lose 5.25. I know I rounded off to 5.24, but 5.25 volts across the bottom 10 ohm resistor, and that leaves exactly 1.52 volts between these 2 points right here. So I've got 1.52. It should really be 1.5 volts because of the way I rounded. 1.52 volts across those three resistors. Okay, so let's show how we can use that to figure out the current in each one of those branches. Okay, so here we are. We know we've got a voltage drop of 1.52 volts across the three parallel branches there. We know what the resistance is in each branch. We can now figure out what the current is in each branch. So starting with the furthest left branch, I'm going to start with this branch over here, right there. V, and I'll just call it the left branch, VL equals IL RL, or I in the left branch equals V divided by the resistance in that branch. The V is the same for all three resistors. That's a characteristic of resistors in parallel. The voltage drop across the the voltage across the branches in parallel is always the same. In this case, 1.52 divided by 20 ohms, and that is going to give me, that is 0.076 amps, which is 76 milliamps. Okay, the middle one, so the current in the middle branch, actually, why am I using a different designation? I should just call that I3. This was I2. I said left, but it was already designated as I2. So I3 is just going to be equal to the voltage across that portion right there, divided by the resistance. Same voltage across all three, 1.52 volts, divided by, in this case, 5 ohms. So you should expect there will be more current in that branch because it has the least amount of resistance. And in fact, it's got 0.304 amps, which is 304 milliamps. Now that you know 2 out of the 3, you can find the last one, I4, by simply finding the difference between, remember what our equation was at the beginning, I1 has to be the sum of the 3 others, which means now that I know 3 of those 4, the only one I don't know is I4. I could just say I4 is equal to I1 minus I2 and I3 added together, which, let's see what that is. I'll come down here on the right again. I4 is going to be equal to 0.525 minus the sum of 0.076 and 0.304, which is, let's see, 0.145 amps, which is 145 milliamps. Okay, so we've got the amount of current in each branch. I know it seemed really long and really complicated, but what we basically applied were the rules for finding equivalent resistance in a circuit, in a series and parallel circuit, and we did it systematically to be able to reduce the resistance down to one single resistor for the whole circuit. Then we used that to find I1, and once we had I1, we were able to use the knowledge of the current coming into that branch and knowing the voltage drop across those two 5 ohm resistors on top to figure out what the voltage was at this point right here and at this point down here, so that we knew the voltage drop across the three branches being 1.52. Okay, I will have at least one more screencast. I might have a couple more screencasts on circuits to highlight a couple more concepts that you'll need to know for the AP test.